Today we're going to talk about separation of variables, which is a technique for solving differential equations. I would recommend that you treat this just like we were in class, so grab a sheet of paper and take notes as we go. Solving a differential equation analytically. That just means solving it using the algebraic skills that we know from anti-differentiation. So for example, solving this differential equation dy dx equals 2x. That means finding the original function whose derivative was 2x. And so this one's pretty easy. To solve this differential equation, we say y must have been the antiderivative of 2x, which is x squared plus any constant. So that's your answer to solving this differential equation analytically. It gets a little bit more complicated, though, if we have a differential equation that looks like this. We've already talked about two ways to solve this differential equation numerically. One of those is a slope field. We don't know how to solve this differential equation yet because of that y. And so we can use a slope field to plot some slopes and see what the solution looks like. On Friday, last Friday, you learned how to approximate a solution using Euler's method. So as long as we have a starting point, some initial condition, we can build the solution out to another point and approximate the solution that way. Today, however, we're going to be looking at how to actually solve this differential equation analytically, just like we did with this previous example, by anti-differentiating. But again, it's a little tricky because of that y. We're going to use a technique called separation of variables. What that means is literally to separate your variables. What we're going to do first is move the y's with dy dx and move the x's to the other side. So we're going to separate our variables. We're going to get our y's on the side of the equation with dy dx, and we're going to leave our x's on the other side. The key here is that we can only move the y's and the x's with multiplication or division. So looking at this one, it makes sense that we can move this y over by multiplying it to the other side. And we get y times dy dx equals 2x. Now you can see that my variables are separated. I have the y with the dy dx and the 2x on the other side. My next step is going to be to integrate both sides with respect to x. So what that means is that I'm literally going to draw an integral sign and say, what's the derivative of y dy dx with respect to x? And that needs to be equal to the integral of 2x with respect to x. You can see that whatever I did to one side of the equation, I did to the other. This next step goes back to the idea of undoing implicit differentiation. If we look at that integral, you can see that in order to get y dy dx as my integrand, some sort of implicit differentiation took place. And what that means is that we can sort of disregard the dy dx. Our antiderivative is going to be the same as just anti-differentiating y with respect to y. It's not really algebraically correct, but you can sort of think about it as those dx's canceling out. And then we can also integrate this side with respect to x. Now we can just anti-differentiate each side. The antiderivative of y with respect to y is 1/2 y squared. The antiderivative of 2x with respect to x is x squared. And we're going to add our plus c on that right side. Usually, actually, I call this C1 because I'm going to manipulate that constant as I solve for my original function. Usually the goal is to get y or y squared by itself. So I'm going to multiply both sides of the equation by 2 and get y squared equals 2x squared. And then I can multiply C1 by 2, but that just turns it into a different constant, which I'm going to call C2. And then I could solve for y, but getting the squared off of a y sometimes makes it more complicated because I have to do plus or minus. So I'm actually just going to leave my final equation as y squared equals 2x squared plus c. That is my original function that had the differential equation dy dx equals 2x over y. So this is the solution to that differential equation. We can actually check this solution by implicit differentiation. So again, this is a solution that we just found. Let's find its derivative by implicitly differentiating. So if we differentiate 2y, we get 2y dy dx. If we differentiate 2x squared, we get 4x. And if we differentiate c, we get 0. Solving for dy dx, we get dy dx equals 4x over 2y, which equals 2x over y. And if we look back to our original problem, that is the differential equation we are given. So we can see that it did work, that we were able to find the original relation between x and y. Let's try another one. Dy dx equals y squared. Again, we can't solve this differential equation, quote unquote, normally because it has a y in it. So our options are to draw a slope field, to use Euler's method if we have an initial condition, or now we know this new technique of separation of variables. So my first step is going to be to get all my y's with the dy dx and anything that's not a y on the other side. Remember, though, that I can only do that with multiplication or division. So I'm going to multiply both sides of the equation by 1 over y squared, or divide by y squared. And get 1 over y squared dy dx equals 1. Now you can see that my variables are separated, that I have my y's with the dy dx, and then I have everything else on the other side. My next step is to integrate both sides. I know that when I integrate this left side with respect to x, the dx's are sort of going to cancel out. So it's just 1 over y squared dy equals the integral of 1 dx. Now I can anti-differentiate both sides. The antiderivative of 1 over y squared, if I bring it to the top, y to the negative 2, add 1, and multiply by the reciprocal, I get negative 1 over y equals, the antiderivative of 1 is just x, plus some constant. And remember, I call it C1 so that I can manipulate it later. Now to solve for y, that's always my goal, is to solve for y or y squared. I'm going to multiply both sides of the equation by y. and then divide by x plus c1. And since I'm not changing it anymore, I'm just going to call it plus c. And so this is my solution. My original equation was -1 over x plus c. Again, I can check by implicitly differentiating. To do that, I'm going to rewrite this as x plus c -1. And actually, on this one, I don't even need to implicitly differentiate. I just get dy dx. I can use chain rule here. So I'm going to bring down the -1 and get a +1. Leave the x plus c alone to the -2. So I get 1 over x plus c squared, which, if you look at the original function, is equivalent to y squared. And that is the differential equation that I started with. We're going to pause for a second on these separation of variables to talk about some vocabulary that you probably first heard about in Math 1 and Math 2. And that's this idea of proportionality. If we say that y is directly proportional to x, the way that we write that mathematically is that y is another way to say equals. Directly proportional to x means there's some constant times x that describes this relationship. What you can see is that if x increases, y also increases proportionally. And that's what it means to be directly proportional. If we say y is inversely proportional to x, that means y is inversely proportional means some constant divided by x. And what that means is that if x increases, y actually decreases, and vice versa. The reason that I wanted to go over that is that many times on the AP exam, they won't actually write out the differential equation for you, but they'll tell it to you in words, and it's your job to write the differential equation itself. That happens a lot with growth and decay models. So what this means is that if we are told the rate of change of y with respect to t is directly proportional to y, we can actually write these words as a differential equation. For example, the rate of change of y with respect to t, we know we can write as dy dt is an equal sign directly proportional to y. That means that some constant multiplied by y. If you look at this, we don't know how to solve this differential equation just by looking at it because of that y that's in our equation. But we know that we can actually solve this by separating our variables. So let's try that. I want to move the y to do with the dy dt and leave everything else on the other side. Remember, I can only move by multiplication, so I'm going to multiply both sides of the equation by 1 over y. Leave the k on the other side. Now that my variables are separated, I'm going to integrate both sides with respect to t. When I do that, the dt's are going to go away, and I'm just going to be left with dy. And on this side, I'm integrating k with respect to t. Now I can anti-differentiate both sides, and I get natural log of the absolute value of y equals kt plus some constant, which I'm going to call C1, since I might change it later on as I solve for y. And here's the point where I want to solve for y. To get y by itself, I have to undo natural log. And as we've talked about a lot in this class, the inverse of natural log is an exponential function. So I'm going to exponentiate both sides of the equation and do e to the natural log of the absolute value of y equals e to the kt plus C1. Because e and natural log are inverse operations, I'm just left with the absolute value of y. And that equals e to the kt plus C1, which I'm going to write as e to the kt times e to the C1 using my properties of exponents. If you see here, because e and e have the same base, you can add their exponents to get what we originally had. The reason I'm doing that is because this is just some big constant. And because it's just some big constant, I'm going to call it C2. And for the ease of looking at this problem, I'm going to move it to the front. So it's just some C2 times e to the kt. Now I'm really close to solving for y. All I have to do is get the absolute values off. And the way I can do this is just let the right side of my equation be either positive or negative, which in and of itself can just be engulfed into C2, which is just an even bigger constant. And so I'm going to write as my final answer y equals some big constant e to the kt. And that's the solution to my differential equation. Sorry. dy dt equals ky. Let's try another one that acts sort of like the one that we had before. dy dx equals x squared times y minus 1. My goal here is to separate my variables using multiplication. So I'm going to have 1 over y minus 1. That's what I'm going to multiply both sides by. dy dx equals x squared. My next step is to integrate both sides with respect to x, which really is the same thing as integrating this left side with respect to y. As I anti-differentiate, the antiderivative of 1 over y minus 1 is the natural log of the absolute value of y minus 1. And the antiderivative of x squared with respect to x is 1/3 x cubed plus some constant. Now, I want to get y by itself. So I'm going to exponentiate both sides. That means that I'm just left with the absolute value of y minus 1 on the left. And I'm going to I'm going to separate these powers using multiplication. I can now, because I have this big constant right here, just bring it to the front as some giant constant C2 times e to the 1/3 x cubed. I can take the absolute value sign off and sort of let them be absorbed by my constant. So now I'm just going to call it C. And my final step is that I need to add 1 to get y by itself. And so my final solution is C e to the 1/3 x cubed plus 1. That was my original function. Do another example. I have the differential equation x squared plus 4 dy dx equals x times y. This one's a little bit more complicated, but the idea stays the same. I want to move everything that doesn't have a y to the right and everything that does have a y to the left to be with the dy dx. So first, what I'm going to do is divide both sides by x squared plus 4. And then to get this y to the left-hand side, I'm going to multiply both sides by 1 over y. So now my variables are separated. I have 1 over y dy dx equals x over x squared plus 4. I'm going to integrate both sides with respect to x, which really is integrating the left with respect to y. And now I'm going to anti-differentiate. The antiderivative of 1 over y is the natural log of the absolute value of y. And here on the right side, we have x over x squared plus 4, which I hope you can see is a pretty simple u substitution problem. Use x squared plus 4, du equals qx dx. And so I can rewrite this as 1/2 times the integral of 1 over u du. And so I get natural log of the absolute value of y equals 1/2 natural log of the absolute value of u, but remember, u is x squared plus 4. And then I have to add c1 on the end. I'm going to exponentiate both sides. I know if I exponentiate this side, I get just the absolute value of y. And if I exponentiate the right side, I'm going to go ahead and have e to the c1 out front times e to the 1/2 natural log of x squared plus 4. You do have to be careful here. This e and this natural log don't undo each other yet because of this 1/2 that's sitting there. So we're going to have to do a little bit of manipulation to get rid of that 1/2. What we can do to make it better is to rewrite it as a square root. So we're going to write this as the absolute value of y. I'm going to turn this into a big constant c2 times e to the natural log of the square root of x squared plus 4. Taking that 1/2, using it as a power, and writing it as a square root. That means that we can now write it as the square root of x squared plus 4 because the e and the natural log will undo each other. And then I'm going to let my absolute value be absorbed into my final constant. So y equals c times the square root of x squared plus 4. Now I want you to try one. The differential equation dy dx equals 3x to the 4th times y squared. I want you to pause the video now and try it on your own. But when you unpause, I will start working through the solution so that you can check your work as you go. So to separate my variables, I'm going to divide both sides by y squared, which is the same thing as multiplying by 1 over y squared. Now that my variables are separated, I'm going to integrate both sides. The antiderivative of 1 over y squared is negative 1 over y, and the antiderivative of 3x to the 4th is 3/5 x to the 5th plus some constant. So now that I have antidifferentiated, my last step is to solve for y. I'm going to multiply the y over, and then divide to get y equals. I do have y equals here, but it doesn't look very pretty. I have that double-decker fraction in the 3/5. So I'm going to multiply the top and the bottom by 5 to make it a little prettier and get negative 5 over 3x to the 5th. And then I'm going to absorb that 5 in my big constant. So this is my final answer. Negative 5 over 3x to the 5th plus c. Our last example is going to be finding a particular solution. That means that we're actually going to solve like we did normally, and then use our point to solve for c. So what we're going to do is separate our variables. I'm going to multiply both sides of the equation by 1 over y minus 2. Now that my variables are separated, I'm going to integrate both sides. The antiderivative of 1 over y minus 2 is the natural log of the absolute value of y minus 2. The antiderivative of 4x is 2x squared plus some constant. To get y by itself, I'm going to exponentiate both sides, and I'm going to skip some steps here. I know if I exponentiate the left-hand side, I'm going to get y minus 2. And here, I'm going to get e to the 2x squared with some big constant out front. If you need a step of how I got that constant, go back to some of the previous examples. And then I can add 2 to both sides. to get my general solution. CE to the 2x squared plus 2. However, I'm not going to stop here because I am given the initial point, y of 0 equals 5. So I'm going to plug in 0 for x, set it equal to 5, and solve for c. That means that I have c e to the 0 plus 2 equals 5. E to the 0 is just 1, so c plus 2 equals 5, and c equals 3. Therefore, my final solution, my particular solution, is y equals 3 e to the 2x squared plus 2. Now I would recommend that you try these 4 problems on your own. If you notice 1, 2, and 4, you should get a particular solution. On number 3, you're going to get a general solution. I would pause the video now and work through these 4 problems. When you unpause the video, you'll see the answers. Here are the answers to those problems. If you notice in number 1 and number 3, I don't solve for y, I just solve for y squared, and that's fine. When you try to solve for y, you get plus or minus, which sometimes makes it even more complicated. If you have questions about these 4, please feel free to email me. I'm happy to answer your questions. Your assignment for after you try those 4 practice problems are sections 6.2 and 6.3 in your book, and the Solving Differential Equations handout, which I will post on our class website. Again, if you have questions about these, please feel free to email me.